everyone. I'm Adami. I'm a professor of microbiology and molecular genetics and physics and astronomy. And we have a phone call here at Michigan State University, and let's answer it first. Okay. And I've been part of Beacon for 2 years. First year as a visiting faculty on sabbatical, and I liked it so much that I decided to stay. I'm going to talk to you about some work I did with Aaron Tinzer. Go ahead. And somebody wants to come in, I think.
It's not coming in the right way.
All right. So which button do I push for when that happens for the third time? Okay.
To unknown. Make sure it's unknown.
Okay. As you see from the title, it has to do with game theory and it has to do with evolution. And I and Aaron have been working on evolutionary game theory. So, this is the type of stuff that we do. What we did was we saw a paper that appeared very recently in the Proceedings of the National Academy, authored by Bill Press, who I believe was once the chair of AAAS or something like that, and Freeman Dyson, who is a very well-known theoretical physicist, one of the co-inventors of quantum field theory, and who has been branching out in all kinds of different sciences recently, and in this case in the game theory. And I should let you know that Bill Press is a respectable age, but of course Freeman Dyson is at a much more respectable age. But in fact, the math that I'm going to show you is entirely his. So I think that's quite astonishing. So what is it about this paper? It says here that the iterated prisoner's dilemma contains strategies that dominate any evolutionary opponent. In order to tell you what we have done in response to this paper, I have to tell you about the prisoner's dilemma, about what iterated means, what strategy is, what domination is, but evolution you already know, so I don't have to explain that. So, once we read this title, we figured, really? I mean, because if you read through this paper, you get the impression that they seem to imply that there are strategies that will win every evolutionary race against any other strategy, in particular, that evolution can't create that strategy. Now, when they used the word evolution, they always had sort of, air quotes around it. But to some extent, I had done some work with Aaron and a grad student where we had, in fact, been evolving strategies, and we knew for a fact that this couldn't be true. So then we basically sat down and said, okay, so what are we going to do? Let's understand this paper and then write our own paper. You may also want to take a look that this paper was contributed by Bill Press to the proceedings, which means, because he's a member of the National Academy, and so is Freeman Dyson, and I, by the way, not. If you contribute a paper to the National Academy, it still has to get peer-reviewed, but I believe you do get to choose the reviews. And we'll talk about that perhaps a little bit later. So, when this paper came out, there was a lot of stuff happening in the blogosphere. Here's an article by Tech Review. They are talking about the emerging revolution in game theory, and they're saying that the world of game theory is currently on fire. Because what was described there was not thought to be possible. And I'm going to tell you what it is that they described there. Basically, they said Press and Dyson discovered a previously unknown strategy for the game of prisoner's dilemma that guarantees one player a better outcome than the other. So, for you to get a better idea of what this is all about, I'm going to give you a little bit of an introduction to game theory. So first of all, history. Evolutionary game theory didn't start out as evolutionary game theory, but simply as a theory of games and economic behavior. And it was written by two people. One is Oskar Morgenstern, who was an economist, and the other is John von Neumann, who many people believe, me included, that he may have been the smartest person ever to walk this planet. He was fluent in ancient Greek and Latin at age 5. I have a daughter who's 5. She is not fluent in ancient Greek or Latin. He, of course, as we all know, was a mathematician who also invented the foundations of quantum physics, quantum mechanics, almost foresaw information theory, you know, in 1940 something, or actually earlier than that, 1935. Of course, also invented the computer. Is the father of artificial life and many other things. But also he decided at one point that he should actually invent the theory of games, which he did. But some of the central concepts of what game theory is today are actually lacking from this. And it is only the modern versions of game theory you know, that have actually made an impact, and that's evolutionary game theory. So evolutionary game theory is this theory you know, of games applied to populations of players, not to individual players. And there the idea was that you want to understand the tensions between cooperation and cheating behavior to understand why animals and by extension humans are cooperating. And these are pictures of the main players in this game, starting perhaps with Robert Axelrod, and maybe Travis and Hamilton, then Axelrod, and then finally people like Michael Novak, Carl Zygmunt, Sir Robert May, and John Maynard Smith. I sent our article, by the way, to both of these people, and they were very nice to comment on them. So it is this theory that actually came out of the old theory, but in fact, the old theory ended up never really being applied to economics, yet the new theory of evolutionary game theory, people later actually did apply to markets to try to understand rational decision making. If you want to get an introduction to game theory, evolutionary game theory, I suggest reading this book. This is John Maynard Smith's book. That is really the most introductory, and it's not too complicated. I could understand it, so that means all of you can too. So let me introduce you to the central concepts before I can go on to explain the Zde strategy and then what we did with it. The central concept of game theory is the strategy. The strategy means different things, whether or not you're talking about deterministic games, so like games where you might play always the same move, or always the same move in response to somebody else's move. And then a strategy is really just one out of a set of moves. Okay? Let's say like playing, you know, the ace of spades would be one strategy. But there are also probabilistic games where there's a probability to play a certain card or a certain move, and that could also be in reaction to somebody else's play. And then you would call a strategy the set of probabilities, which is not the same thing as, you know, a move. So one has to be careful what we call a strategy. They sort of use interchangeably. So now the central point that it came about actually after publication of John von Neumann's paper is that there is this thing called an optimal strategy. Okay? And this optimal strategy is known or set to resolve all conflicts. And that's the strategy where neither party can improve their outcome by unilaterally switching strategy or move. In other words, that it is the move that, given all possible moves of my opponent, gives me the best outcome. And if my opponent also chooses, you know, their move that way, then we end up having the rational strategy. And that rational strategy is known as the Nash equilibrium point of game theory. This global solution. Nash, in fact, went to John von Neumann and showed him, you know, his paper where he had derived, you know, via some mathematics, the Nash equilibrium point. And John von Neumann, of course, would look at that and say, isn't it trivial? Isn't it just an application of the probably Hausdorff fixed point theorem? And the answer is, on the one hand, yes, it is trivial. But then again, if it's trivial for John von Neumann, doesn't mean it's trivial for everybody, because after all, you know, John Nash did get his Nobel Prize precisely for that trivial thing. So this Nash equilibrium point is a fixed point, and it is, in a sense, the strategy that I am going to go to once I optimize, you know, my moves. The only trouble is that it doesn't necessarily have to be a stable attractor or a fixed point. It can, in fact, be an unstable point. Okay? So from the evolutionary point of view, it's maybe not that interesting to just have a fixed point, because in evolution you would probably want to go to a stable fixed point. And This is the contribution of John Maynard Smith. He knew about Nash equilibrium point, but he wanted to know, in a population of strategies, who will emerge victorious? And it turns out that that is what is known as the evolutionary stable strategy, or ESS. That's John Maynard Smith's contribution. And this concept is distinct from the Nash equilibrium because you can show that even though every ESS must be a Nash equilibrium, so this strategy fixed point, not every Nash equilibrium needs to be an ESS because the ESSs are the stable ones. So basically what an ESS is a Nash equilibrium point that is also stable. So I will now introduce a prisoner's dilemma and then show you what is the ESS in the prisoner's dilemma, and I will also teach you how to actually calculate a ESS for any game. Okay, that's going to be important here. So the prisoner's dilemma, many of you can be possibly familiar with it, but here's the idea: two criminals commit a crime together. Okay, and then the police actually sees them fleeing, so they know these guys are very suspicious. But they can't just, arrest both of them because it could be that one or neither of them actually did it. So, what do? They both get put into the slammer and then they're interrogated separately. Now, if both remain silent, then the police will probably go like, fine, I'll get you for speeding for actually, leaving the scene, but we can't tell if any of you actually did it. So, if they don't rat each other out, they basically, get a reduced sentence. That's this case here. But of course, this remaining silent is not the only option. You could basically imagine that one guy says, look, in exchange for me to actually not spend a year in prison for speeding, which is excessive, but then again, maybe this is Texas. Or maybe not Texas, Oklahoma. Then, they cut a deal and say, like, it was, the other guy and I go free, right? So there is, in fact, a temptation to testify against the other one. And if they both testify against each other, they go like, look, we know that it was, it was you because the other guys said so, but then they basically both get 5 years, okay? But the other possibility is where one testifies and the other one remains silent, one goes scot-free and the other one gets the full sentence. They don't get the full sentence here because they still don't know exactly who it was, but they know it was one of them. So that's the general game idea that was given. But the main point is that Nash equilibrium says this is the optimal decision to testify. Even though it would be better for the group if they both kept silent. And this idea of having penalties is usually actually turned around where you're talking about payoffs. So here the payoff of both defecting, which is the testifying, is low, and the payoff of both remaining silent, meaning cooperating, is high. And here's this temptation bonus for this player here. The defector gets 5, and the cooperator, in fact, gets nothing. So this is what is typically called a payoff matrix. And the payoff matrix is written in such a way, usually, that the payoff goes to the row player. Okay? So in other words, it is D that gets 1 here, and it's the C player who gets 0. And here it is the D player who gets 5. So always keep in mind, when I see a matrix like that, that the payoff is the payoff to the row player, not to the column player. And the Nash equilibrium point is, in fact, this here. Okay? So now I'm going to actually show you how to find an ESS rather than a Nash equilibrium point, because in evolution, that's the point where that you should be going. So generally think of a payoff matrix of n possible moves. Okay, so move 1, move 2, move n, and this is the opponent's move 1, move 2, move n, and this would be the payoff for move 1 playing against move 1. So if we had C and D as a 2-strategy game, then this would be the payoff for cooperation and cooperation, and this for defection versus defection. And here's the idea is the following. A strategy is the ESS if, in fact, this formula holds. We don't have to look at the formula, I'll just show you. Basically, you look at the diagonal element of that strategy, and you're looking if it's larger than any other of these elements. That means that this is the payoff for player 1. If I if my payoff playing against the same move is larger than I would get playing any other move against one, then in fact this is the ESS. Or here, if this diagonal element is larger than any of the other elements in here, then in fact that is the ESS. If there's another element that is larger, then this is not the ESS. Okay. Sometimes there is no ESS in a strategy, in a game, and sometimes there is one, sometimes there's more. Okay. Now there's another case where, which is important when looking at stability. Sometimes, so you can do this, sometimes what can happen is that rather than a diagonal element being larger than any of the elements in the column, it could be the same. So in terms of dominance, if an element is largest, then it says that that move dominates all the other moves. But you could have a thing called weak dominance, where in fact it is larger or equal. Like for example, let's say this is larger than all the other ones, but there's one element that is in fact as large. So in order to understand who wins then, the question is whether or not this element, my payoff against that alternative best move, is larger than this one. So in other words, if I have an equality, then I have to look whether this one is larger than that. And we'll encounter this in a moment. Once you know that, you know how to find an ESS for any game that can be written in terms of a payoff matrix like that. So, for example, here's a payoff matrix for the prisoner's dilemma. What is the ESS? Well, here's a diagonal element. Is it larger than diagonal than anybody else in the column? No. Here's a diagonal element. Is it larger than the column? Yes. Hence, this is the ESS, and it is in fact the defection is both ESS and Nash equilibrium in the prisoner's dilemma. The reason why there is a dilemma in the first place is because, in fact, of this temptation payoff. It's high. If this would be 3 or lower, then there would, in fact, not be a dilemma because both of these strategies could be stable equilibrium times. All right, now let's move from this very simple game of I'm going to play one particular move all the time to probabilistic strategies where you would say, okay, there's a probability to engage in the play C, and then of course then you would have a probability of defection would be 1 minus that. Okay? But it turns out that if you go to prisoner's dilemma, the ESS is still that that you do not cooperate, even if you have a probabilistic strategy. The defection is still selected for as the correct strategy. But suppose players play more than one game against each other. Because in this case it was always, we play one thing, and then that's all. Okay, who wins? But then the question is, if you more than one play is played, what happens? Well, if past plays are ignored, then the outcome will always be the same. Because I always start a new game, and I'm just like, okay, what am I going to do? Defect. Okay? So nothing happens in the prisoner's dilemma if the past is ignored, in the prisoner's dilemma if the past is ignored. But if decisions are influenced by the past, everything changes. In fact, defection suddenly is not the ESS anymore. There are cases where, in fact, a cooperation is favored. In fact, it becomes possible because if the plays depend on other people's plays in the past, I need to basically know about them. They need to be communicated to me. That means the players start communicating. Cooperation becomes possible because if decisions are influenced by the past, that really means players communicate. And if you think about it, that ought to have been trivial from the very beginning, because there is not a single example in either the animal world or the microbial world where you see communication in the absence of, cooperation in the absence of communication. All right, so let's talk about strategies that take into account previous moves. So that could be as simple as reactive strategies where you take into account the opponent's last move. So then, I'll show you what happens then. And then there's other things called memory 1 strategies where you take into account the opponent's and your own last move. Okay? I mean, you can't just remember things just because you did them. In principle, memory means you communicate to yourself. So in the case of reactive strategies, instead of just simply having a single probability to cooperate, now I get 2 conditional probabilities. Namely, the probability to cooperate when my opponent in the last move cooperated, or the probability to cooperate given my opponent in the last move defected. So now a strategy becomes 2 probabilities. So for memory 1 strategies, actually this single probability becomes 4. because it's a probability to cooperate given that I cooperated and my opponent cooperated. Given that I cooperated and my opponent defected. So in memory 1 strategies, there are 4 probabilities that define your strategy. And we might ask, what is now the ESS? And it turns out that question is actually a very sophisticated question. And I would say had not been fully solved, but I think we know it now. We'll get to it. So what I will be doing is I will be calling these 4 probabilities P1 to P4. So P1 will always be the probability to cooperate if we both cooperate, and P4 will always be the probability that that cooperated if we both defected in the previous move. By the way, memory 2 strategies also, where you remember not just the last move. You can have much more sophisticated strategies, but I'm not going to talk about them. So now I want to show you that it's possible to calculate the expected return of an infinite encounter between 2 strategies that evolve that use probabilities. Okay? It's actually very easy to understand how you do that. I'll give you an example for a reactive strategy. In fact, I'll give you an example for the strategy tit for tat, which says, if my opponent played cooperate in the previous move, I'm going to cooperate. If my opponent in the previous move defected, I'm going to defect. Hence tit for tat. So the idea is, so here's tit for tat strategy, here is the opponent's move, and whatever the opponent's move is, that's a different strategy than tit for tat. Okay? The idea is, I'm going to now show you, what happens to the accumulated payoff over time as they are playing. I mean, this is the payoff to the tit for tat player, and this is the payoff to the other strategy. Okay? So it's always, again, the payoff to the role player. So let's say they start by cooperating, and then everybody has a mean payoff of 3, and then they continue cooperating, and so basically you keep a tally, and it's always 3. But suppose in the next move the opposing strategy defects, then in fact TFT gets a 0 averaged in, whereas the defector gets a 5 averaged in, and you see that the average has changed now. Okay? And then it goes on. Now this is a tit-for-tat player, right? So he always plays what the other guy played. So this guy played D, so then he's going to play D. And in this case, they both play D. That means you get 1, averaged in, and so on. Okay? So this basically updates. And you can imagine that if they play an infinite number of games, that these things become stationary. In other words, they're not going to change anymore. And so these are the numbers that we're going to be playing with. This is now the stationary payoff given strategy P and Q that are encoded in these vectors like this. I'm going to call this the function f of P and Q and the function g of P and Q. And the general trick that Dyson and Preston employed is that they were able to calculate these things for certain strategies. And I'll show you how that works. So we're going to go right into these zero determinant strategies, and I'm not going to talk about why they're called zero determinant because that's mathematical. And we're going to do it for this payoff matrix where the cooperation payoff is called R. This is called the sucker payoff for being suckered into cooperation when the other one defects. This is the temptation payoff, and this is the payoff that you get if you both defect, RSTP. And then basically the idea is of the Zde strategy. Remember there's 4 probabilities. Choose 2 of them as a function of the other 2 and as a function of these 4 payoffs. That is, when you do this, that's the Zde strategy. Okay? Now how Freeman Dyson came up with it is a long story, but he did. Okay? He thought of this, and you see that there's some really very curious properties of having chosen these exactly in this manner. So let's actually look what happens if you choose this standard payoff instead of these arbitrary numbers. And then basically it's a fairly simple relationship that eliminates 2 of these probabilities. You still have to choose 2 other ones, but you can't choose them freely. You can actually show that P1 must be kind of close to 1 and P4 must be close to 0. Otherwise, they will not be probabilities. You would find in here that these things would become smaller than 0 or larger than 1. Okay? But these if this is true, then this defines a family of strategies that are all of the same kind, of the ZD kind. Okay? And one thing I want to show is that if this is the case, then it's clear that ZD tends to cooperate if both players cooperated in the previous move, and it tends to defect if both players defected in the previous move. Okay, so that's sort of qualitatively what these strategies do. So now let's calculate the expected payoffs. And it was, Freeman Dyson who taught us how to do so, using a method, that uses actually determinants. So here I'm going to show you what the payoff is to the ZD player playing the other strategy. And it's a function of these 8 probabilities P and Q. And this is in fact the function G, which is the payoff to the other guy, the non-ZD guy. So in general, this function here is a complicated function, well actually not of P1, P2, P3, because P2 and P3 have been eliminated. So the only 3 parameters are these 6 probabilities and these 4 payoffs. The formula for this function, which is what the ZD player gets, is actually not in the Press and Dyson paper. So I have to go sit down and calculate it myself. So it is not a simple formula. In fact, you cannot even write it into the paper. It's that complex. But mathematics actually can do that. So this is a very complicated function. What about the payoff to the other guy? That's this function G. It's this. It's very different from the expression that you saw before, even though there's really just one asymmetry about who is whom. And it is a very simple formula, and you should take a look. It does not depend on Q, even though this is the payoff to the guy with the strategy Q. It doesn't depend on Q. That's what the ZD strategy does. It gives a payoff to the other player that does not depend on the other player's strategy. The other player is ripped off, possibly. In fact, it's exactly ripped off if the ZD payoff is in fact larger than the other payoff. Because the other guy can try to change strategy. So like, oh my God, I'm getting this low payoff, and you're getting all this. I'm going to move, I'm going to change, I'm going to, cooperate or defect. It doesn't matter. That strategy cannot do anything against the payoff that at the end of this infinite game is being handed to him. So basically the idea is not of a prisoner's dilemma, but basically, one is the rip-off and the other one basically is screwed. So, let me show you a typical ZD strategy. I put in, let's say, a P1 of 0.99 and a P4 of 0.01. Remember, this has to be close to 1. This has to be close to 0. And we'll be choosing this one all the time. It's one example. The results don't depend on that. And so if you plug it in there, you basically get these values. So here's a typical ZD strategy. Okay? It, in fact, almost looks like a either I always cooperate or always defect type of strategy. But it's not quite that. Okay. All right. Now let's take a look at what happens. So actually, let me introduce extortioners too, because I've shown you that ZD strategies can unilaterally set any opponent's payoff. But there's another type of strategy that Press and Dyson discovered that extort, and I call them ZDE strategies. Basically, they are such that the payoff of the other guy now does depend on his own strategy Q, but the ZD player, which is slightly different, it's a ZDE strategy, it's a bit different than the ZD strategy, can make it such that his payoff is always a multiplier of the other guy's. So in other words, if this guy is 1, I can set my strategy so that my payoff is always 3 times yours. The only fair game would be if that multiplier is 1. And here is what happens. So while in fact the payoff of the other depends on Q, so this opponent here can go like, all right, so you're extorting me, fine, but I'm going to change my strategy so that I get a higher payoff. I can now do this because now my payoff does depend on my own strategy. But what happens is that as the other player increases their payoff, this payoff increases commensurately because what's fixed now is the multiplier. So I go from a payoff of 1 to 2, and I see that my opponent goes from 3 to 6. Not fair. And this is in fact the central point of the idea that ZD strategies can dominate any evolutionary opponent, because what they said is here's in fact one of these other strategies, and here it's doing a hill climbing to increase, in an evolutionary way, its payoff. But what you see, and these are 10 different runs of different ZDE strategies. You see that the opponent, as a ZD strategist, increases the payoff commensurately. So in other words, evolution can never reach it. But I want to show you one thing. What this is really here is the optimization of the payoff of the other against ZDE, and this is the optimization of this. But in evolutionary game theory, that's not sufficient in order to determine who is actually the evolutionary winner. This is what we talked about before. Who is the evolutionary winner is determined by what is the evolutionary stable strategy, not how much the pairwise payoffs are. Okay? And in fact, that has to do with the concept of dominance again. Here, what you see is that this dominates that, possibly, okay? But in fact, it does not show you whether in fact there would be an alternative best reply. Okay? So, a strategy said to be dominant is better than another strategy for one player irrespective of what the other players is, but it's only called weakly dominant if it's better or equal to another strategy. And in fact, another theorem of Maynard-Smith is that weakly dominant strategies are not necessarily ESSs. This essentially are jumping off points. Because what Arndt and I did is, well, we can calculate these stationary payoffs. But once we're done, in a sense, that says that that's almost like we just played one game against each other. So let's just put them into a payoff matrix. Okay? Because that's what happened. And then these two functions are these two. That's the function that does not depend on O's strategy Q. So that's the forced payoff to O. And this is this very complicated function that I wrote down there, which is the payoff to the ZD player when he plays O. That does depend on both of these things. But in order to find out who is going to be selected by evolution, I need the diagonal elements. Right? Okay, so what are these? We know that ZD forces any strategy to take f of p. So what does ZD get if it plays against ZD? Well, because it doesn't depend what the other strategy is, ZD is getting f of p himself. Okay, so let's put it in. Now, what about this here? Well, that's the payoff of the other to play other. And, that depends entirely only on O. On his, he sets his own payoff, so it's a function only of Q. Now let's find the ESS, and we can do that actually very easily looking at this. Let's try it. So, what about ZD? Okay, well ZD is going to be ESS if that's larger than that. Well, it's not. In fact, they are equal, so that means in fact there's weak dominance. And then, if they're equal, I just have to see whether this is larger than that. So actually there's an even simpler trick. You can show that you can subtract a constant from every column and still get the same exact ESSs. So let's do that. It's called bringing it into a normal form. And once you're doing that, you're subtracting f from here, subtracting h from here, and you see f has completely disappeared. It just shows you that this forced payoff is not going to play any role in determining who actually wins the competition. Whoever wins the competition depends only on the sign of this. Namely, whether the payoff that ZD gets versus O is larger than what O gets against himself. But since O can set their own payoff to themselves, like for example, always cooperating, I can make sure that this is always larger than that. So in other words, ZD ought not to have any chance of winning unless the other strategy really plays very poorly with itself, like always defective. So, generally, ZD will lose against most strategies that play well against themselves. Okay? Let's see here. Give you an example. We're taking this example strategy. There, f is equal to 2. Just plug it into that formula that I showed you. And I give you an example opponent strategy, which is called Pavlov, or win, stay, lose, shift, which is a very well-known strategy from the iterated prisoner's dilemma literature. For that, in fact, it's very simple. It's the 1001. not going to go into why it's called Pavlov. You can think about it, about the when state is shifted, essentially this state. And I can plug this into our formulas, and I can get all these other numbers. So first of all, you see immediately that, that Pavlov is always going to cooperate with itself. Okay? So h of q is 3. That's the big cooperation pair. Okay? And I can calculate for you that the payoff to the Zde player in that complicated formula ends up to be just 11 over 27. So it's 2.46. So 2.46 is larger than 2. So then my matrix looks like this. Zd, the other strategy gets 2, Zd gets 2.45. So Zd wins every direct battle between the two strategies. Yet, we know how to calculate the ESS. It's not this one, I have to look, what's larger, and this is larger, this is the ESS. For Zd to be ESS, this number would have to be larger than that. So it wins every confrontation, yet in fact is going to lose the population game. So this one's ESS, this one's not, because they are in fact only weakly done. Okay, well, so game over. I mean, but we decided to anyway test it with a differential equation approach to see indeed what the competition between the strategies is, and this is in fact what happens. If you look at the population fraction between the Zd player in blue and the Pavlov player in green, whatever the initial conditions are, Zd goes down, even though it wins every single confrontation. Question? Yeah?
The Zd player can still modify his own strategy, right?
No, they can't, because you have to P1, P2, P3, P4 are fixed if you're a Zd player. You could modify within the Zd class, yes. You could do that to try to maximize your payoff.
Right.
In fact, we've never actually looked at that. How we would do that, but you could in principle look for the optimal Zd strategy, but it's probably only optimal given a particular opponent, because it does depend on both P and Q. Okay, so clearly Zd is not a winner as you might have imagined, and indeed in this blog post that talked about the emerging revolution in game theory, and that the world of game theory and fire, it actually turns out that that was their figure number 1. It was actually a blog post about Arendt and mine paper, because what they're saying is, well, not so fast, Preston Dyson, because winning isn't everything, which was in fact the title of our paper. I could have shown you a little bit more that in fact, if you say, well, what you found with this replicator equation and with these infinite payoffs, maybe that's not what's going on if actual agents are playing this game against each other in a finite population and where these games are not infinitely long. Well, we actually know how to program that too, and it turns out while the dynamics is a bit different, basically the same result holds. So this is not a result that is due to the fact that we're playing infinite numbers of games that there's an infinite population and so on. So there's a very robust effect. The Zd strategy cannot win, in this case, against power, or when state is short. Now, you could say, well, what is the optimal strategy? And, aren't there some strategies that Zd is going to win against? So, if you want to know what the optimal strategy is for one particular player, in this case the other player, because, it's obviously not going to be Zd, what you can do is you can do an evolutionary algorithm where you're trying to optimize these 4 probabilities. But if you're going to do it in an agent-based manner where actual agents are playing with each other, you actually have to have a 5th probability for the first move in the game where there's no history. Okay? So basically what we do is we encode these just like as loci, in an evolutionary algorithm. And by the way, this is a 2-bit communication channel really, because you're getting information out of 2 sources. And then you would say, okay, I'm starting out my evolutionary simulation with random choices. Basically, the probability to cooperate is just 1/2. And then you're making evolution and asking, where will this go to? And that would be our evolutionary fixed point. Now, the Nash theory doesn't actually tell you where that would go, and in fact also the ESS theory of Maynard Smith is not written for conditional strategies. Okay? So essentially, the only way to discover what the optimal point is that you actually run the simulation. And if you do that, what happens is that indeed you're going towards a particular fixed point. Okay, this is one particular one, don't worry about what these numbers mean. But I want to make sure that you understand that just because there is a fixed point doesn't mean that the strategist will just sit there and always play this. You know, there's a population, and because what I play depends on who else, you know, what other plays are going on in the population. It turns out that the strategists sort of form clouds around that fixed point, you know, and they can oscillate back and forth.
Does that only happen if that's actually ESS? Because if it's not ESS, it will...
So, the concept of ESS is not well defined for conditional strategies, unless you actually say that you define it just the way I did, namely that you're taking the iterated payoff as the one-shot payoff and then look for the ESS. So,
even in that case, you would have infinitely many strategies.
That's right. That's right. So you can't really write down that huge table, but there may be a way of trying to understand. We've never done this. Trying to understand, you know, whether in fact the fixed points that we do find, whether they have a chance of being an ESS of the iterated game. But so the idea here is that we want to understand, you know, an evolutionary trajectory going from a random strategy towards a selected strategy, and we want to ask, well, where is Zde there? I mean, you know, would it ever actually have a chance of being anywhere near this fixed point? So first of all, this is how this would look like. So I'm not showing you how all 5 probabilities change over time, because that's a 5-dimensional picture, and I don't know about you, I have trouble visualizing that. But what you can do is you can do a principal component reduction into the first 2 principal components, and then you see, starting at the random strategy, that as evolution goes on, you move in a very specific path towards a particular fixed point. And this is in fact a low mutation rate fixed point. So the discovery in this paper was that the fixed point actually depends on the mutation rate very strongly. Because in fact the high mutation rate fixed point lies over there, and it's a defector, and at low mutation rate it's a cooperator. And it was not that difficult to understand why this is the case once you understand that cooperation occurs because of communication. And if the mutation rate is low, the communication channel is actually quite good. But if the mutation rate is high, then, you know, the strategy I'm playing with is constantly being mutated, and the information that's being transmitted to me is actually not information but entropy, because the plays do not reflect necessarily the genes if there's a high mutation rate. This is why high mutation rate defection is, in fact, the fixed point. So now we know, for example, at high mutation rate, what the fixed point is. Okay. Now, and by the way, all these other strategies, tit for tat, win, stay, lose, shift, they have nothing to do with an evolutionary trajectory, a true evolutionary trajectory. They are just artifacts of not doing evolution. But you can read about that in this paper. So here is a plot of the optimal strategy. Here's these 4 P's as a function of mutation rate. So this shows you that at low mutation rate you get high cooperation, and at low mutation rate you get a high defection. Okay? And we could just pick a mutation rate here and then take a look at this strategy defined by these 4 numbers. Okay? These 4 numbers. And we can say, well, let's take a look at what the payoffs are. And I'm going to show you in one moment why did I choose this one. The reason I chose this one is that if I plug this into this matrix, I find that, okay, I have to check. So if I want to know whether Zd is the ESS, I have to see whether this is larger than that. And it is. In this case, because this is smaller, this GC, general cooperator we called it, is in fact dominated, strictly dominated by Zd. But how can this be? As we have just shown that Zd is not the evolutionary fixed point, but GC. Yet Zd seems to be ESS. Well, the only way to resolve this is you go and do the experiment. So what you do is you start a population with all GC. No, sorry, we started with all ZD. And then maybe you introduce, well, whatever, but basically you see what happens to ZD when you turn on evolution. Okay? If it is, in fact, the overall best strategy, then it should just stay. So this is what I just said. ZD is in fact ESS, so let's do the experiment. So you start the population, and this is basically just these 4 probabilities as a function of time, and here's ZD, the particular ZD, which has a high P1, low P4, and I believe high P2 and low P3 or something like that. And what you see is that very quickly, the population moves away from using that strategy and ends up at the point GC, which we already knew was going to happen. But it is strange, right? Because GC would lose if it would be faced directly with ZD in the absence of mutation. If it was just between the 2 strategies, then ZD would win. But that's not how evolution works. The way evolution works is that immediately there's mutations to the ZD strategy, which then suddenly are not ZD strategies. Because you have to have a very specific set, of P's to be a ZD strategy. And as I showed you, ZD actually loses against most other strategies that play well against themselves. So, very quickly there are mutants of ZD that beat ZD. They're not GC, but they are mutants that beat ZD. So ZD is actually mutationally unstable. It is sitting on a peak that is maybe admittedly high, but in fact any mutation away of it is going to basically create a very low fitness for ZD. And as a consequence, it's really on a very high, narrow peak, and as we know, because of survival of the flattest, that you can be easily outcompeted by more robust strategies, even if they are in fact less fit. And in a sense, I've shown you that GC is in a sense less fit, because it would lose in a direct competition in the absence of mutation. So ZD strictly dominates GC, but in a true evolutionary sense, it is unstable. It evolves into GC. So ZD, therefore, is not only not an evolutionary stable strategy in many cases, it is also unstable in a different way, namely it's mutationally unstable. So, is there no advantage, therefore, to a zero-determinant strategy? Well, there could be. Just imagine, the Achilles heel of ZD was that it had to play against itself, and then it basically is stuck with the same payoff as the opponent. What if, in fact, ZD could say, well, I'm going to play ZD against all those that are not ZD, but I'm going to cooperate with myself. Then I have to be able to recognize, other strategies. Okay? And there's actually at least two ways that I can think of, how a strategy could recognize another one. There could just be a tag that I'm going to be reading. A tag is just another bit of information, as a play that I'm using for making conditional decisions. It's just a piece of information. And people have worked on tag-based strategies before. Or, in fact, a ZD strategy could have a longer memory than just one move. If the other player only has a single memory, then I could, probe the other strategy and see whether I get back things that are conditional on 2 moves, or whether I get back, which is sort of like a marginalization, an average. And then I could see whether this is a memory 2 strategy I'm playing against, or a memory 1 strategy, and that would give me the information necessary. But in both cases, that actually implies that ZD only has a chance if it has more information than the other strategy. Because if you write down the ESS, the payoff matrix for a ZD strategy with information, well, yes, it will win or can win against O, but not if O actually also has information. If O also has information, there's information equality, then O is again most likely going to win. So in other words, what is going on here is that if there is an informational advantage, there is a selective pressure for the exploited one to either cheat and by, for example, imitating the tag that ZD uses to recognize itself, And so that, you know, it just waves, hey, I'm ZD because I get cooperated with if I'm ZD, and then that advantage goes out of the window. Or else there's a selective pressure to also, you know, acquire the ability to distinguish self from non-self. So all this would be is an evolutionary arms race, which is of course what we end up observing with any trait. In this case, whether ZD strategist or not, it's all about information. So, lessons that we learned. And I think this is an important lesson that was brought up here also. It looks like the stability of iterated games can be understood in terms of the payoff in the stationary state by writing down this equivalent one-shot payoff matrix. And as far as I know, this was not done before. Another lesson is that weak dominance is not sufficient for evolutionary stability, and you know, this was known for a long time, but there hasn't really ever been, as far as I remember, a striking application of that. The Zde strategy, because of forcing the payoff to be the same for both the Zde strategist and the opponent, you know, the weak dominance is the key element in the stability. And the third point is that even strictly dominant strategies can be unstable at finite mutation rates, which is, you know, a version of the survival of the flattest effect, which we discovered in 2001 using, of course, Avida. So let me recapitulate what we've learned. So first of all, the discovery of Zde strategies itself I find very interesting. I mean, it's really a curious mathematical accident that you can do this. But the second lesson is that even if you can do this, you know, it's important to pay attention to actual evolutionary dynamics, and you can realize that just because you can win every game, it doesn't mean you win the race. And actually, as a side note, the Zde strategy was actually discovered quite a bit earlier by Carl Sigmund and Martin Nowak, but they wrote this up in an obscure paper that only garnered 3 citations because it was in a journal that nobody ever read, and was only rediscovered when Martin Nowak, I believe, or else Carl Sigmund, saw this paper and was like, haven't I seen this before? So it is new, but it isn't really new. And the way by which Nowak and Sigmund found these strategies is actually quite a bit different, radically different, in fact, than the way Freeman Dyson has done it. But the last lesson is, even if you're 88, you can still, you know, do a ton of really cool mathematics. So at this point, let me thank my collaborators on this project. Arendt, of course, you know, this paper was really a co-production between the two of us, and then my former grad student Dimitris had been working with Arendt and me on the evolution of these conditional stochastic strategies. And at this point, let me thank you, and we have time for 5 minutes. Of questions?
I have one.
Go ahead, Bill.
So you mentioned a couple of slides ago the tag-based strategies and one other thing under which Zde might, I didn't catch this.
The tag-based or memory-based?
Right. What about those under mutation though?
Good question. My suspicion. So first of all, mutation now can have several effects. Mutation can affect both the probability to engaging in action, but it can also affect the tag. The tag must be a genetic object. And as a consequence, you can either evolve away from it, or in fact have purifying selection to make sure that you're keeping it. But if you find, for example, that the opponent is imitating the tag, then there's a selective pressure, in fact, for the Zde strategists to evolve a new tag that they're going to be agreeing upon.
But suppose the tag is perfect and nothing mutates both the two kinds.
So
then Zde does not become GC?
So I don't think we know the answer to that. We haven't tried it. Arendt, can you speculate?
The question is if you cannot mutate the
tag, but you can mutate the probabilities.
Yeah, but I mean, just noise in that system will take care of one tag existent alone, and then it's obsolete to have a tag. I mean, and that if you have an agent-based model with finite population size, and you do not mutate tags, you will only end up having one tag alone, and then tag becomes obsolete. Then the question is, who makes the race to win the tag? And there I have no answer. So you have to, you have to make the tag mutation. You have to mutate the tag, otherwise
basically the opponent dies out.
Yeah.
And then there's no need for it.
Any questions from other places? Ben?
Go ahead, Ben. Oh,
Your sound?
Can't hear you.
Hold on.
Use sign language.
Ben, your sound isn't coming through.
Smoke signals go.
Just answer something.
There. Why would
Just guess what Ben would have asked.
20%, can we beat it?
Okay, we're getting help.
It's
He's watching.
Are you on mute, Ben?
Can you hear me now?
Yes.
There you go.
Okay. Sorry. I'm on in stereo and multiple mics now. I just was going to say that was very interesting, and I'm just curious. That's just a small question about whether or not whether there's any hope of being able to analytically map the space of the opponent's probability set. So it's such that, under what analytic conditions does the opponent play well enough with itself that it can beat a ZD strategy? So is there any hope of sort of getting some sense of that the size or fraction of the space of possible strategies that actually can? I mean, can this be beaten any which way, or are there only certain strategies, a small fraction of the set of strategies that can beat it, or is there any hope of getting some analytic grasp on that?
So I don't know whether or not. So first of all, I think it's actually the majority of strategies, because all you have to do is really play well against yourself. But as I showed you, that if you're doing that, it affects the payoff of the ZD player. So and it's the relationship between the two. So it's a complex thing. But the way these strategies were discovered is that Bill Press did a computer simulation. And he thought, I have a big computer, I'm going to map the whole space of strategies, I'm going to find out who is ESS, since there is no theory that tells you what it is. And what he found out is there were these huge neutral areas, which are exactly those where the opponent's strategy doesn't matter. So the payoff is the same. And basically what happens is his computer would constantly crash. This is retold in some blog post somewhere, because of these huge neutral areas. So what Bill did, according to this blog post, he called up or saw Freeman Dyson, and he says, "Look, Freeman, look at this." And he said, "Okay, I'll look at this," and then a week later sent him the formula. So it's like, here, this is why this is crashing. There are these strategies which are these hyperplanes, of constant payoff. Now, having said this, we do have the formula for the actual payoff of one versus the other. But as you saw, it is extremely complex. Now, if you actually put in the values R, S, T, and P, the formula actually does fit on a page. And it is not inconceivable that, some bounds can be made, on this. But I think it requires someone with a bit more temerity than I have.
I think it's actually quite easy, because you only want to know how well you play against yourself to be better than against the ZD strategy.
Yeah. So basically you have to make a bound, of this H of Q larger than F, and then see, if you can somehow bound it. I think that would be interesting, but maybe academically interesting only, because we know that ZD is a loser. Thanks, Ben.
Since we're short of time, any from other places?
Yeah, so I'm trying to interpret your results in terms of possible, maybe implying limitations for the use of evolutionary algorithms when trying to find the best strategy for some game. do you think that your results do imply limitations, such as, you know, you're basically using the wrong method if you want to evolve the best chess player, because there might be some really outstanding strategies in chess that you could never evolve?
Yeah, so the point here is that, you know, President Dyson did use an evolutionary algorithm to optimize, you know, the strategy of the other player versus the D player, in particular the extortionate ones. But, you know, this is not the right, you know, framework when you're talking about populations, because in populations, how you play yourself is important. And what Arendt and I had shown earlier was an evolutionary algorithm will, in fact, you know, if you make it a population-based one, find the optimal strategies. So you could ask, for example, you know, yes, is it the absolute, you know, highest point? But in fact, it depends on the environmental conditions. So in an evolutionary setting, you know, there are other things that play a role than just what my genotype is. It's also what the other genotypes are, or resource abundance and so on. So in a real setting, you can't just do a brute force optimization and there is no solution, because the solution depends on many other things, in particular who you're playing with and the entire makeup of the entire population. So once you're doing this right, you're going to get solutions, but the solutions are going to be specific to the conditions that you're in. In chess,
it's fair to say that evolution could discover Zd, but it would not stay if you continue evolving beyond that.
Yeah, that's right. So under certain circumstances, evolution could discover Zd, but only at extremely small mutation rate. It's this idea of, can you climb these narrow, high fitness peaks? And the answer is not if there is a flatter peak anywhere nearby. You won't even discover that. But in principle, there is a path. It's just a path that evolution is not going to take.
Can I ask the last question?
Sure.
So far about all the strategies that we talked about are really discrete or mutually exclusive type of strategies. Is there any framework that would account for the plasticity of strategies? For example, on the defecting strategy background, with mutation or some just physiological plasticity, you generally get some cooperative components into this this background.
So I want to, you know, so the question here is, you know, whether you can have a non-genetic aspect of a strategy, because, you know, these genomes here are probabilities, conditional probabilities. But I want to make sure that it's clear that there is also an environmental aspect of this strategy, because in fact they react to the plays of others. So they are in fact plastic. But you could imagine that, you know, it could be plastic on other aspects than just the other plays. You can make probabilities conditional on, for example, other tags or other elements of the environment. So in principle, you can easily encode any influence on the phenotype, how I play. But it has to be, in the end, genetically encoded, because obviously all phenotypic plasticity ultimately still has to be genetically encoded, right? So it's easy to do that, but in fact, it's not usually done. I mean, what I've shown you is pretty much as far as people go when doing evolutionary game theory. They do conditional stochastic strategies with memory 1 or memory 2, possibly with tags, and that's it. But you could actually, for any interesting situation that might be interesting to you, include phenotypic plasticity based on an environmental variable that you control. It's possible to do that.
You mean learning?
You could even, you know, introduce learning, sure.
If there's any more questions, we'll take one more from afar. We have access to Chris here, so since we're nearly out of time. Anybody else?
If you had a leaders in your evolutionary algorithm that changed the results here, would you then, you know, stay at that Zde strategy?
I don't think so, because the mutants of the Zde strategies are actually, they're outcompeting them in numbers. So evolution is a population effect, obviously, and it's not just that they have some sort of a small, advantage that, because of a small population size, could be drifting. They really have a disadvantage, and as a consequence, elitism, is not going to sustain them.
Anybody else?
So, do you have a sense of the feasibility of memory-based strategies, or do you just need such sampling to have any idea if it's in that ZD range, if your opponent's in the ZD range to...
Oh, you mean tag-based?
No, memory-based.
Oh, memory-based. We've never actually played around with that. I mean, it's a pure hypothesis that this can be done. I'm pretty sure it can be done, but we've certainly never evolved a strategy that uses memory in order to distinguish that. That would be an entirely new paper by itself, and that's very interesting. We just never have played around with something like that. It's actually easy to do, because we can set up, a confrontation between a player with memory 2 and another group of players with memory 1, and then having the ability to distinguish others is always going to be beneficial to you. Like, the idea is information is always beneficial. So will you then see an evolution to a strategy that sort of pings the opponent and then compares the result with the expected results, and then sees, I know who you are. I'm not playing against myself here, I'm playing against the other. I think that would be an interesting paper if one could pull that off.
Okay, we better bring it to the end. Thanks again.
Thank you.